Okay, so let's talk about theropods again. Let me turn off the lights so we can actually look at this. So we've talked now about theropods, and primarily the focus of the theropod discussion so far has been large theropods. I've used T-Rexes a lot of examples, and that's partially because we know so much about it, and that's partially because it's such a charismatic animal, not actually because we have that many specimens of it. But there's a lot of information on it relative to some of the other large members just because of that bias. Today what we're going to do is we're going to move from the larger theropods, so the animals that people commonly think of dinosaurs, and we're really going to look at small theropods and the way that we know that they're linked to birds. So I've entitled this, this is the rise of birds, right? So this follows your book, but the reasoning behind that is because this really is an explanation as to why we see certain characteristics in dinosaurs and how we know that birds and dinosaurs are closely related. So this animal that you're looking at right now, I think most people would probably call this a bird. And actually, this is not a modern bird. This is another group of birds that we haven't talked about yet, and we're not going to talk about in this particular lecture. But I just want to give you some idea about the diversity that surrounds these small theropods, right? There's a lot of diversity within that, and the small group that we think of, oh, those are obviously birds, is actually just a small segment of that diversity, but fit within the larger complex, right? It really does look like a gradient of less bird-like to birds, basically, and that's one of the ways that we know. Now for you guys, this is sort of elementary stuff. Birds are dinosaurs. We already talked about this in the course. We've gone over it multiple times. But you have to keep in mind again that when I was growing up as a kid, birds and dinosaurs were separate things. They were not one and the same, and so reiterating it is important. But we also have to understand why that birds are dinosaurs. Actually, the idea that birds were dinosaurs is a fairly old idea, so that was proposed in the 1800s. And the 1800s is actually, you may say, well, that's not that old. But keep in mind, evolutionary thought only developed in the 1860s, right? The published idea of evolution as formed from natural selection really doesn't occur until the mid to late 1800s. And that was not shortly thereafter that the idea of, well, birds then therefore are feathered dinosaurs in that sense. But if you remember back to some of the videos we've seen also, you can really start to see the struggle between that, right? Birds as dinosaurs, but the animals that they're conceptually are dinosaurs are these lumbering, brutish, something like a giant reptile. How can that also be a bird, right? Very different animals. So what ended up actually happening is that idea was largely, by the larger scientific community, was discarded as the explanation for where what lineage dinosaurs arose from, and people largely considered, well, dinosaurs are archosaurs, but they're probably a separate lineage within that. We're not really sure how they sit next to birds, so we're not entirely clear about that. But that idea actually, and you've seen a lot of this guy already, in 1986 was proposed in a paper by Bacher that dinosaurs were, which should include aves, right? That aves should be subsumed into Dinosauria. And that is part of his, you often see him talk about why do we think dinosaurs are warm-blooded or endothermic? Why do we think of them as active? Why are they the same as why does he compare them to modern mammals? Why does he talk about digestion a lot? Why does he think about predator-prey ratios? He was one of the minds that was really thinking, well, if birds and dinosaurs are really closely related, then what happens when you expand that out, and what does that mean for those communities, right, and for those ecosystems? And so what we're going to do today is we're going to step through how we actually know this relationship. So up until now, you have, by and large, taken it by faith that birds and dinosaurs are the same. You've seen some relationships that suggest, yes, they are very closely related, not least of which is I keep mentioning that feathers are not that rare in the dinosaurs, right? Like they are in a lot of dinosaurs. But so that should give you a pretty good indication that they are related, because you don't see feathers on lots of different things, right? We don't go outside today and we say, well, birds have feathers, but so do these tiny snakes, also very feathered. That's just not, that doesn't happen. When you go outside, by default, if you see an animal with a feather, you know that's a bird, right? There is no other animal with a feather. So that should be a very good indication to us of the relatedness of those animals. Here's the one that I've already talked about. Of course, feathers are today in modern aves groups. are incredibly complex structures, right? They're not a simple thing. They're actually a fairly complex a piece of structure on these animals. They always have what is this central vein, the rachis, which is a sturdy support element. And then around the rachis, they have these barbs, which form, again, a relatively sturdy support system. But the important part here is extremely lightweight, right? Feathers are very, 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 very lightweight, which is really useful for flying animals. Now, don't get me wrong, that doesn't mean that therefore feathers evolve for flight. In fact, we're going to talk about why feathers evolve, and it's almost certainly not for flight, okay? Because there's no intermediate stage between having no feathers, like a truly scaleless lizard, and having enough feathers to just be able to fly, right? That's not a good intermediate. You'd either have to have lots of feathers or none at all, and so there has to be another explanation for how feathers evolved in that case. So flight is not sufficient for that. But look at the complexity of this. You've got all sorts. This is the most complex type of feather we have currently. It's an asymmetrical flight feather. Of course, by me saying it's asymmetrical, you know it's asymmetrical, but that alone is a fairly complex structure. It's got lots of interlocking barbs, which form a structure. The structure is very important, and the actual complexity of building that item is very important. You can also note that it's not symmetrical top to bottom, that the top of the feather has different elements than the bottom of the feather, and those are grown from the animal skin, right? So there's a lot of complexity involved with this particular element. Feathers, of course, currently are used for flight in a lot of cases, but they actually have many other uses as well. So what are some other uses for feathers in modern groups?
Insulation.
Insulation is really important. What else?
Sexual selection.
Sexual selection is really important. What other things?
Protection, like the pet.
They can be used to provide some protection to the body elements. Yep.
The cuticle makes them so when they are swimming or diving down to get food, that the water droplets come off.
It can help the waterproof them. Yep. These are all elements of feathers. There's also actually another one I'm thinking of. Larger, yeah, there's some predator deterrence there. The other element that's actually useful is not dissimilar from the way whiskers are used. So feathers around the face of birds actually have a sensory perception. They provide information for close-in physical objects to the bird's face. So if the bird, obviously eyes don't work when you get really, really close, right? The distance between this and this for my eye is not very effective at telling me that. But if I have a tiny whisker that comes out, I get very fine knowledge about how close an item is to my eye. Or to my face, so feathers can also be used in that way. So those are just some of the ideas, right? So feathers are useful for lots of things. We just think about them in the context of flight because a lot of groups do use them for flight, but there's many other reasons to be feathered. Oh. And then other characteristics of aves as a group, right? Certainly for all modern aves, there's no teeth, complete loss of teeth. Birds actually do have genes for teeth. You can express them if you know the right codes to turn on in embryos, and you can produce dinosaur teeth in birds, right? I mean, they're simple peg teeth that repeat. They're theropod teeth. They repeat over and over again. You can turn those on in beaks and actually produce teeth within beaks, but all modern aves by default do not have teeth. Birds are also relatively large-brained. You probably know that because we interact with birds in a very different way than we do with other pets, right? Bird pets are very different from some of the other pets. It doesn't mean that birds are the smartest animals on the planet. Mammals really seem to have picked that up, but not very many mammals are really that smart. Only a few members are probably relatively intelligent, and so by comparison, birds are also a relatively intelligent group. And certainly compared to basal members of aves, the modern birds are very, very smart within that. They've also got a couple of pieces within the skeleton that are important, not least of which is this bone, the carpometacarpus. They are also, this isn't a bone, but they are also bipedal, and the tibia and fibula are unequal and partially fused within them as well. These are all characteristics. So let's look at some of those. Here's the carpometacarpus. Carpometacarpus is actually in what would be the hand of the bird. Bird hands are actually used to help in flight. They are still designed from the five-digit element of the primitive ancestor, right? For whatever reason, it's not clear why this is the case. All modern quadrupeds are evolved from members with 5 fingers, right? We all share this 5-finger body plan, and it's a modified version of this that produces more or less fingers, right? You don't get more fingers because you have 30 fingers that appear out here. You get more fingers from a 5-fingered ancestor. In that sense, you actually have to build those out again. And you get weird situations like with pandas, right, where they lose a digit and then they don't re-evolve the digit. They just modify a bone to accommodate some similar functionality of that. Anyway, metacarpus here is actually the fusion of multiple fingers within the hand. So you can think this bone here is really a combinational bone of different fingers that are aligned so tightly now that they can't separate from one another. And that's why what appears to be such a large finger, the birds have one really long, what looks like pointer finger, and then they have this little bit that sticks out here. That's actually, that the name is, you won't forget this, is called the bastard wing, and it is useful actually in flight. It helps to, by small changes in that location, you can cause stalling elements to occur and get very strong control of flight by that.
So is that similar to bats? How they're like fuse fingers and whatnot make up their...
So it's similar in the sense that when you get into flight, there's a problem. You want really strong elements because flight requires very, very strong forces because the body weight is what you actually have to lift up off the ground. So you have to actually physically push down the amount of air, the amount of energy, right? You have to support yourself on your fingers. But you also want to be concerned about weight. So evolution for flight is obsessively compulsive about getting rid of weight. Everywhere it can, it wants to strip weight away. If it's in bones, if it's in organs, if it's in brain size, it wants to strip weight out of the body as quickly as possible, and you see that. So fusion is really nice because what it does is it reduces the number of spaces between bones, which add a lot of weight to the animal. It also strengthens those bones because they are no longer multiple elements that can wiggle side by side, but physically can be tucked together and locked in a single unit, so they move as a single unit. But the disadvantage, of course, is you lose flexibility. But for an animal that's flying, that may not be very important in that way. So that it's convergent in that sense. Does that make sense? Birds have been around longer than bats and probably flying for longer. So they seem to have some elements that they have a longer history of those elements within that. And then the thing that we've looked at a number of times now is bird feet. This up at the top right is a classic bird foot. It is probably about the same as a bird foot in a dinosaur that you think of, a primitive theropod. Probably the scales are arranged in much the same, if not the same fashion, and the coloring is probably similar in many of these animals to primitive members of this group as well. The difference here is that bird feet often have a fourth digit that sits well back, and it forms a nice grasping element so the bird can perch. But it's not that theropods didn't have 4 digits, it's just that digit tended to be a little bit further back and smaller. Birds have made that much, much larger. That does impede some locomotion on the ground when it's very, very large, and that's why it would have been moved further back up along the leg in more primitive theropods that spend more time on the ground, but it provides a really nice way to hold on to branches so that you're not constantly spinning around. Right? What it does is prevents you from having to constantly reposition yourself slightly, so it saves you on that way. And then if you look at the leg, there's a lot of stuff going on here. Let's see, I'll just use my little bit of chalk. First of all, look at the pubis and the ischium. Really weird looking Saurischian pelvis, right? Because it doesn't look anything like the Saurischian pelvis you've looked at before. Not least of which because the ischium is teeny tiny. It's that little tiny bone that comes down and folds up against it. But you can see that there is why would there be an opening between the ischium and the pubis? Well, because the ischium has migrated backwards and connects now with the pubis, right? So these are they appear as 2 separate bones, but then reconnect and fuse into one in that sense in the embryo. You have a standard femur, and then it gets weird again. There's a patella for your kneecap. But what you have here, look at this, the tibiotarsus, right, is a fused tibia and upper bones of the foot have actually fused together. And the fibula is a little tiny sticky bone, right? It's like a toothpick of a bone that sticks out to the side. And then down here, you haven't seen it yet, but the tarso-metatarsus is also unique to birds, and we'll look at where that comes from. So let's look at that tiny fibula. This is apparently an Asian cooking site that I found, but what's nice about this Asian cooking site is she did a really good job of removing, I know it's she because it says Mama Lee, so I'm assuming it's a woman. removed the muscle and left behind the bones, but they're articulated together so you can actually see them located. And look how tiny and thin that is, right? So if you eat chicken drumsticks, sometimes you get what looks like a little bone toothpick. That's that fibula, and that has been so reduced in size again. Again, reduction in size and weight, and increase in the strength of one element within that. Unlike your leg, right, where you have 1 plus 2. Again, let's go. We also have other things. I showed you that, but I haven't talked about it yet. Tarso-metatarsus, pygostyle, pneumatic bones is characteristic of aves, but remember that extends far back into the Archosaurian lineage, and certainly all theropods had it. They also have, for birds, modern aves, they have a relatively rigid skeleton, and associated with that are these adaptations. And then last of all, for modern birds, is a very distinctive and obvious location for flight musculature, which theropods would not have had because you don't need to grow what are effectively enlarged breast muscles if you're not doing lots of active flying. There's no need to put on that much weight. That just makes you really, really strong at bringing your arms together like you're a power clapper or something. So theropods did not have, I should say primitive theropods do not have that. The group that we have today is using that flapping motion to provide lift, and so they are therefore enlarged beyond what they would have been. Let's look at the tarso-metatarsus. The tarso-metatarsus is also a really weird bone. It's the fusion of 3 bones in the foot region, and as a result, because these bones fuse back together, there are these weird openings between them, right? Because the primitive condition is to have them separate, and then they get fused back into one bone. Pygostyles are actually the tail of theropods. What happens in chicks is that as the tail is growing, there's a gene that turns on and kills all of the subsequent cells behind it. And when it does that, they lose their tail. But before they lose that, they develop this very sticky, or this very large and basically fused section of that vertebral column out there, and that forms the butt of the bird. And it's also that element which those feathers that stick out from the tail are, the things like a turkey, right, have feathers, and when they wiggle, right, that's what you're seeing wiggle. They're wiggling the pygostyle. So it's not actually terribly different to some degree from the way in which a theropod could have wiggled its tail. A little bit different now because the muscles are much smaller. And the synsacrum is this fusion of the pelvis into one element with the vertebrae on the back of the body to a large degree. And again, this is very similar to what you mentioned before in flying animals. We see a lot of fusion of bones. What you don't want in flight, so imagine you're trying to fly something like an airplane, and you have elements that tend to wiggle a lot, right? What you're going to end up happening is spending a lot of energy because you're going to be making a lot of drag as different elements are moving independently of each other. If, on the other hand, you produce very strongly coupled elements that are stiff to one another, they will not wiggle much, and you will spend less energy on drag because you'll have less turbulent currents behind you in that sense. So birds are a largely fused dinosaur, right? So a lot of the bones that we would look for are now fused into other bones, and instead of having lots of bones, actually birds are nice because they have fewer bones in that sense. Different names, but fewer bones. And then, of course, within birds, they have pneumatic bones. People used to say, well, they have pneumatic bones because they fly. If you get rid of a lot of the crap in the middle, then they become lighter. That's not true. Birds have pneumatic bones because theropods have pneumatic bones, and theropods have pneumatic bones because a primitive archosaur member started to incorporate components of the lung, which were air sacs, and allowed more unidirectional flow of air, which increased the efficiency of that breathing. And so birds are lucky enough to inherit pneumatic bones, and that is a great element, but it doesn't, therefore, that is not the reason that flight evolved, or that pneumatic bones evolved was not to accommodate flight. Pneumatic bones evolved first, and that assisted when the flight was actually picked up later in that group. And the other group that would have pneumatic bones that also attain flight in the Archosaurs, pterosaurs also have pneumatic bones, and they would have functioned probably the same way that modern birds do, providing that one-way unidirectional flow of air and also stripping weight out of the body itself and helping to reduce the overall weight of the animal. And these are not, people think of these as really, really weak. These are not weak. These bones are strong relative to what they are. People think of them as weak because often when you find bird bones, they're small, they're not large. And they still suffer from the same thing that all bones do, which is that bones are relatively inflexible, right? The flexibility that you get in your body is provided by joints and by muscles. That's where your flexibility is stored. Bones are really great if you don't want to compress things. So the reason that I can stand up is because my bones are not being compressed when I stand on top of them. They resist the compression of my body onto them, and that gives me a really nice structure. When I'm sitting down, my legs don't suddenly get longer because my bones relax, right? When I stand up, I'm basically, as far as you're concerned, there is always a small amount of compression, but it's so small you can ignore it. That I'm the same height as I was when I was sitting down, right? So bones are really nice for that kind of stuff if you don't want to do compression. And then let's just look back here. This is that fused element of the vertebrae and the pubis, right? And the pygostyle sitting off the back. I just wanted to highlight it again. And we're going to talk about this giant axe head that's in front of the bird. And the other thing that's important is this coracoid and the furcula. And the furcula is this guy. What is this guy?
Wishbone.
This is a wishbone, yeah. So this, you can call it either one, furcula or the wishbone. Feel free to pass that around. That element of the body is located between what would be where the arms attach to the body. And that is in humans, that is this bone right here that runs down by my neck. It is actually, so you can feel yours. It's very, very large, and it's not a furcula because they're not fused, but that's a clavicle. And the clavicle is really important when you have your arm out. It helps to pull the body back with the arm. So this is a common injury that you get in sports when the arm is stiff and the arm pushes back against the body and the clavicle doesn't flex as a result of that. And instead of having the arm break, even though the forces are initially on the arm, it's transmitted back down to the clavicle, and the clavicle can accommodate that, so it snaps at the neck or in in and around the neck. And that's a painful injury, but it is common. And animals that do a lot of forces with their arms frequently have very, very reduced clavicles, like cats. In fact, cats have vestigial clavicles because they often pounce on things and they're doing a lot of jumping onto their front arms. So it would be relatively risky if forces were uneven that you would constantly be rotating the clavicle in unusual ways, and you could snap it. So cat clavicles are very, very small, and if you dissect a cat, you'll see that because the clavicle is not connected to anything. You actually have to open up muscles to find it, and it's just a little tiny it's a pair of bones, but it's a little tiny pair of bones up in the neck region, but it doesn't have that much functionality. It does still provide some muscle attachment, but it's not very useful in the way that we think of it, where it's really well developed in you, which should give you a pretty good indication that humans are not primarily supposed to wander around on their arms and legs, and also not supposed to be or not supposed to be shoving their arms in large force strength situations out and away from their body, right? It's okay to use them. That's why we have them. They're very useful for that way, but they aren't the way that we think of them where you do a football stiff arm. That's really not how humans evolved. You could do that, but there is a little risk associated with that. And then furculas are very common in dinosaurs. This is a T-Rex, right? Very obviously, also has a furcula, right? So the wishbone is a long-standing element. And if you look at members of these groups, what you'll see is until you get down to very, very primitive members, Coelophysis is around in the Triassic, a relatively primitive theropod, they remain fused. So fusion happened early in these groups, and it persisted throughout the theropod lineage long after that. Birds have just inherited it and modified it slightly. By the way, columba, wherever you see that, that's pigeon. Like the pigeons are the animal that people compare every bird to. So we're going to look at a lot of pigeon stuff, but just be aware that most birds follow this, by and large, this body plan. We're not going to deal with animals that are a little bit different, things like pigeons, right? Or not things like penguins that would be a little bit different because they don't have flight anymore. And then flight musculature. Of course, one of the really important elements for bird flight is that you have really strong breast muscles, because a lot of the strength of the flight comes from the chest, right? You're doing a lot of expansion and contraction to bring the arms up and down, up and down, up and down. Of course, the direction in which you do the most is the downstroke, right? Because you're actually pushing air underneath and away from you to bring you up and into the air. The less strenuous one is the upstroke. And so the upstroke element here has a smaller muscle, but the downstroke has a relatively strong muscle. This is under really tight selective control. You get more power by having a larger muscle, but you also pay for it by having a lot more weight and also having to pay to increase that muscle, which is very expensive to do and maintain. So if you don't need it, you don't get it. And this is why chickens are a good example of a place where we can actually force selection to favor something unusual, you can actually breed chickens that have enormous breast muscles, right? Because that portion of the body is relatively variable. If you need lots of flight, you need relatively large breast muscles. If you don't, they come down very, very quickly. And so that area is variable within the lineage, and we can therefore influence it relatively easily. And chickens, of course, modern factory chickens, of course, do not fly, but they produce large breast muscles, but it's because we select for those. And animals that spend most of their time on the ground, breast muscles disappear or almost entirely gone because you don't need those arms for that much anymore. And then out here, the other thing to see here is that the digits are numbered. So because modern theropods all have the same, or theropods, modern quadrupeds all have the same number of digits. We count with Roman numerals. And of course, that 2 corresponds to your 2 finger, the 3 corresponds to your 3, the 4 corresponds to your 4. But you can see the 4 is now subsumed into the 3, so they're a merged finger now. So when did modern birds evolve? We're going to talk about this. We have a lecture actually on paleonaphans, which are the ostriches, and probably this other group you don't know, the ctenoforms. But that group probably evolved well within the Cretaceous. Right here you can see it's got fairly long error bars which extend from, which actually do cover up some period of the extinction event, but the very early branching members of the modern bird groups are actually well within the Cretaceous, and they're fairly well constrained, so they're about 100 million years ago, and they certainly evolved before the mass extinction event, which means that although you see a lot of diversity in birds, actually some of the diversity was set prior to the extinction event. So many dinosaur lineages went extinct in the extinction event that occurs at the end of the Cretaceous. But multiple modern bird groups actually made it through, and that suggests that therefore birds share some common set of characteristics which are different and helpful for making it through that mass extinction event. No other lineage seems to have made it for the dinosaurs, but this group had multiple lineages make it through, and that is something we'll talk about when we get to the mass extinction event, what gives birds an advantage over maybe other groups of dinosaurs. But this is about when, right, we don't know exactly, but this is about when modern birds evolved. It's actually it's probably what we would call the middle Cretaceous, right? It's fairly obviously suited well within the Cretaceous. But keep in mind, that is modern bird. That means if you went out and saw that bird, you would say, that bird looks very similar to a modern lineage, right? You would have no problem saying that's an aves. That sits within a group that I know. So that means about 100 million years ago, you would have at least been able to identify some of the birds out there, right, as a modern group. Now, that doesn't mean that every, quote, bird that you saw would have fallen within a modern group. In fact, the modern grouping of birds would have been a smaller number of the total population in those ecosystems, but you would have still recognized some of those members. And it also means, right, the members that are close to those modern birds would also have looked similar to some degree. So modern birds must, or I should say, the idea of the bird or the evolution of the bird is a fairly ancient thing. This is a group that's been around a fairly long time, much longer, in fact, than some of our own lineages when we go back, and quite a bit more so. And then if we look at, of course, the most famous member of the group that we think of birds is Archaeopteryx. Now, I do want to be clear, Archaeopteryx does not itself fall into aves. It is not an aves, and we're going to look at why, and very clearly it is not when you look at the skeleton, but it does sit sometime in the late Jurassic. So Archaeopteryx, at least to us, looks like an element of an animal that probably did some flight. So flight must be even older than that for these guys. And that means that it probably evolved no later than the middle Jurassic, at least to some degree, or maybe even in the early Jurassic. So probably as dinosaurs are recovering from this the end Triassic extinction event and leading into the Jurassic, these guys are starting to evolve into animals that you would recognize as taking short flights or smaller glides over that time, right? And so that's a relatively old event when that occurred. So up in the left, I'm going to use this image over and over again, so you're going to have to get used to it for the moment. Up in the left is a reconstruction of Archaeopteryx, and that is reconstructed in the raptor-like pose that you often see theropods produced in. In fact, I like this one a lot because they moved the first toe backwards and use it like a hook toe of what we consider raptors, right? It looks a lot more like a velociraptor in that image, and that's because, of course, this animal belongs to a group that is closely related to the dromaeosaurs, and the dromaeosaurs are the group of velociraptors, the Utah raptors, the dinichids. Those kind of elements are all contained within there. And that doesn't mean that it held the foot in that position. In fact, because this animal appears not to be holding the foot in that position, it suggests that it wouldn't. But it does give you some information. It does at least give you some insight into how similar these animals would be. So, Archaeopteryx, at least at first look, when people found this, right, there was a lot of debate. These were found in the 1800s, shortly after Darwin published Origin of Species. There was a lot of debate about, well, if evolution is true, even if the fossil record is bad, we have to be able to find some intermediate within there. And when Archaeopteryx was found, this was in some ways icing on the cake. It very clearly demonstrated not only do you have a great intermediate between reptiles and birds, but you've even got the feathers preserved such that you can reconstruct the appearance of that animal, at least partially. Although you'll see that our reconstructions weren't great. So let's start with the head first, Archaeopteryx's head. So on the left is the actual, this is actually not the fossil, this is this is actually the fossil animal on that side. But the head here, reconstructed with the artist, you can see it on the right. Couple of weird things about the head. It has lots of holes in it, which again for theropod dinosaurs not unusual, but they are present, right? Lots of openings within the skull, at least in front. You've also got this bony ring of elements that surround the eye. And then, of course, because it's a diapsid, it should have two openings, one on the left, and then for dinosaurs, one roughly on top of the head. And Archaeopteryx does have those. And then, most obviously, this is why this is absolutely not a bird. It's got teeth, right? Modern birds do not have teeth. Archaeopteryx clearly does have teeth, so there's some weird characteristics. Well, if you look at a modern avian skull, okay, first of all, those openings have largely fused together. The last one here, the nares, is still present as a singular, but all the other ones have fused together. Again, that reduces weight, right, because you have less and less bone within the skull. You've also fused the skull on the openings for the musculature of the jaw. By and large, again, that reduces weight. Having lots of different muscles attached to your jaw is really nice, but it also adds a lot of weight. And if you're not spending a lot of time using your jaws to manipulate food items, which birds don't by and large, right? They get the food item, they bring it to the mouth, it goes down into the gut right away. It's away from the mouth, getting it away from the mouth. Then you don't need lots of musculature. And that is also one of the reasons you don't need lots of teeth. Teeth are heavy, and if you're not manipulating food in your mouth very much, then get rid of it, right? And you end up with these very dagger-like and sharp edges that you can use to pierce things, but you're not doing a lot of that manipulation within the mouth anymore. So birds do have elements of a dinosaur skull, but they're very modified in that way. They aren't the primitive aspects we've seen before. Okay, so let's come back to the fossil. Let's look at the arm now. Okay, well, I didn't really blow up the arm, I guess is what I'm saying. But if you look at the arm on Archaeopteryx, there's a couple things to notice here. One, that it has 3 fingers, very distinctly 3 fingers within it. But, and I really like this specimen because both hands have it, which suggests it's not an accident, but in fact the way that they're being held. But notice that 2 of the fingers are being held together, and 1 is being allowed to manipulate outside of that range, right? In both cases, it's the same 2 each time, right? That suggests that the holding of those fingers, the fusion of those bones, is going to start to happen relatively soon. It hasn't happened yet, but the characteristic, the behavior of holding those fingers together is already set within that group. And this other one, you'll also notice, doesn't have feathers associated with it, and it still forms a manipulating structure, right? And so you can still manipulate things with 1, but these other 2 are now acting as a simple, so I have 5 fingers, so ignore the fingers that we don't need, but the other 2 fingers over here are now acting as a single element. And so you can imagine very quickly that if evolution causes these to be fused, that's actually a benefit to the organism, and so we'll see that. So I really think that that alone is somewhat like, oh, that's fairly shocking to think that these animals already by the Middle Jurassic are holding their fingers in a way that we think of modern birds to a degree. Another thing about Archaeopteryx which makes it not what we think of as a bird, but it is still very much dinosaur, is that it has lots of claws hanging off of it, right? Birds do not have claws. That's not actually entirely true, But most modern birds do not have claws that hang off the hands. They add weight, and if you're not going to manipulate things with your hands, you don't need them because you won't need to grasp things. And wings are not really a great grasping tool. They are prone to damage. They have lots of feathers on them, so they can easily get muddied or discolored or damaged in some way from the material that they're interacting with. And they're overly large. Wing arms are really obnoxiously large. You can see here that these arms look large for the body. You know, this animal can reach back and touch its tail very easily with its fingertips, but they're not as large as modern bird wings, which are really, really unusually large on those animals. There's also very clearly asymmetrical feathers within this animal, and asymmetrical feathers, as far as we know, are inherently a product of the selection for flight. And so that suggests that Archaeopteryx, at least to some degree, is using flight as a mechanism to get around, and that asymmetrical feathers by the Middle Jurassic have evolved, which also suggests that feathers must have evolved much earlier than that, because to get to the point where you have an asymmetrical organ like that, or an asymmetrical component of your body like that is very, very complex, you need a long period of time. And then the last thing I pointed out here is that the wrist is now different. So birds have a very unusual wrist because they tucks in really closely to the forearm. This animal also has very distinctly has that wrist, so it's able to tuck the arm in and bring it up close to the side of the body and hold it there against the body to protect both the wing and keep it away from exposure, because the arms are so long, they would be uncomfortably long when the animal's moving, and they might hit things around it. So bring it in close, tuck it in nice and tight. And that's very different from primitive dinosaurs, which really don't have that swivel, and which you don't, right? Your arm does not fold all the way flat to the flush of your arm here very clearly. That would be bad. You would have to snap your wrist. If you're a bird, you actually really do want that, because you really want the space saving of having that up close to your body and having that tuck in very neatly. So that's evolved certainly by this point, and you can see it here, looks very similar to the modern aves, right? So theropods apparently evolved this. So apparently the tucking of the hand up and against the body is a fairly old trait, and that may be because they had relatively long feathers for a long time that they needed to tuck up close to the body when they were moving, and to keep them away from being damaged. And then we're going to also look here at the limb itself, or not the limb, the leg itself. And what you can see about this is that feature of what I mentioned before with the fibula being that little stick bone that hangs off the side. Compsognathus is a fairly primitive member of the group. You can see the fibula is already fairly reduced in size, but it extends the entire length, as is normal. You also remember the metatarsus is a fusion of those bones down in the foot. Here in Compsognathus, they're separate, but look at how close they've already become within that foot. The foot is now getting very, very narrow, and as it does that, the bones get closer and closer together. By the time you get to Archaeopteryx, they're not yet fused, but they function like that, right? They are functioning effectively like that. The fibula remains as some element that looks like a dinosaur. When you get up to Columba, which is, again, the pigeon, then what you end up with is that fibula is far away reduced, almost certainly so, and those bones have now fused within the foot itself. But you can see here, look at the similarity between these feet already. Look at how similar those have already become in that sense. But do look at how different, to some degree, these feet are from each other. Not least of which, because this one's still retaining a digit, a fifth digit there off to the side of the body, right? So this is a fairly primitive theropod that hasn't yet lost all those digits yet. It's a vestigial toe, basically. Not this, even more so than your vestigial pinky toe. Your pinky toe is still relatively large. This probably would not have broken through the skin of the animal, right? It would have been completely surrounded in that case. Or if it did, it would have just been a little bit. I already pointed that out to you, and I pointed that out to you, and I pointed out toes because it's cool. So let's look at the guts of the animal. Oh, you can get in real close that way. I guess I did it that way. One of the things you notice is there's not a giant keel here, right? The keel is useful in modern birds to attach flight musculature to. Very clearly, this animal does not have one. And you might suggest, well, this may be a fossil that's lost that, right? This may have been damaged or lost. But you can see down here, what are these guys down here? Those are the gastrulae. Those are the belly ribs. So no, it hasn't lost them. It doesn't have one. It does not have a keel. It has gastralia, which again is reflective of the primitive condition of theropods. I think this one is also very obvious. I think that the teeth and then here the tail are two of the most obvious conditions that would make you say, that's really a dinosaur that looks like a bird rather than a bird that looks like a dinosaur. But you can start to see how these elements are lost in evolutionary time. Archaeopteryx, of course, retains a very large tail, and it probably functioned as it did in most other theropods, providing musculature attachment for the legs, right, that would come up and reach back into the tail. So this animal, although it looks like a flyer, is actually probably a very good runner, right? So this is an animal that's really intermediate. It, on the one hand, it has elements that make it something of a flyer, and on the other hand, it has elements that retain its primitive characteristics of being a runner. It's not a flyer. It's still acting like a runner, right? If you want to fly, you definitely don't want to bring a really heavy tail with you. What modern flying animal do you know that has a heavy tail? You get rid of those. They don't provide that much support. You don't need lots of muscle attachment out there, and they actually often get in the way in that case. The only group, the Archosaurs, pterosaurs, I should say, that start out with tails, also by and large lose them. The most advanced lineages have just a little vestigial tail that the only real function it has left is just an attachment point for skin. It's not functioning in the sense of it that the primitive Archosaurs used it. And then you can't see it as well up here, but of course this guy has a wishbone. So wishbones, you saw that before. I already cheated and showed you that, but these guys also have wishbones, so the fusion of the clavicle within the chest is already present. And then you'll notice here the Thoracian pelvis. So this Thoracian pelvis is weird because the ischium is pointed backwards, but it's still quite large. And that is also the point, remember, where the gastralia would meet and form the belly of this animal. But it's still very clearly a dinosaur pelvis, right? That's still, you would still recognize that as a pelvis. You would say, it looks something like an ornithischian pelvis to a degree, but it's a little bit unusual because when we see that kind of head and that length and structure, we often think of, oh, well, that's what a Thoracian pelvis would look like, but it looks like somebody broke it and turned it backwards. And that's what's happening. The Thoracian pelvis, not physically being broken, but it is migrating backwards. And as it migrates backwards, it also needs to be reduced in weight because we're attaching less and less musculature to it, and we end up with a modern bird pelvis. And so this is a good example here. This is Archaeopteryx right over here, and this is the pigeon. Again, everyone loves pigeons, but look at how different these pelvises are now. This is really a biped light. This is a very lightly built biped that runs a lot. This is very different. This is the pigeon is very much a flying animal that functions as a biped, right? That is clear, but it's not the same. They're not interchangeable in that way. But clearly, this animal has many of the elements that are going to appear in these much more advanced groups, and so their relatedness, right, is relatively high. Don't be confused. Also, pigeons have that ring of bones around the eye, right? Another characteristic they share with these guys. So the Archaeopteryx in this case is a really good example of sort of exactly what we expect. It should be right in the middle. It should have some characteristics of advanced groups and lots of characteristics of primitive groups, and it should look like it's bad at both, but it's a bridge, right? It's a bridge between very advanced groups that haven't yet evolved and very primitive groups that don't yet have the ability to compete with that animal in the same way. So your book, actually, I really, and this is one of the reasons I picked this book, I think your book does a really good job of maintaining that Aves belongs within dinosaurs, and it gives a good summary in addition to that within this table. So do please have a look at that. And then this I dislike about your book, but that's okay. The book gets a little sidetracked at some point talking about an Evodevo question that seemed to suggest that maybe birds and dinosaurs were different because Evodevo suggested different fingers had evolved to fuse, and that would mean, but the fossil record suggested some other fingers had fused, and that seems to be a combination of different things. The Evodevo turned out to be what we call frame shift mutation, where the fingers actually that we would normally count, 1, 2, 3, 4, 5, the actual genes actually shifted within the framework, so it looked like we were counting the wrong fingers, but it's because two things had happened. One, fingers had been lost and fused together, but two, the actual framework had shifted around within the body itself, and that's fine. But I think it's not necessary for this course to understand that to any real degree. If you're interested in that, Evodevo is incredibly interesting, and you should get involved in that because you'll find there's lots of very cool stuff we can do within Evodevo, and there's lots of very interesting questions we might be able to ask. But we don't need to get too bogged down in this. So when you get to that section, then just you can read it, but don't get too worried. Don't get too hung up on it. So what does this mean about birds? Well, pneumatic bones and feathers certainly did not evolve for flight. They can't. They couldn't have. These animals must have evolved from ancestors that weren't flying. They work really well for that, but that's sort of that's the luck of the draw. They get lucky in that sense, and they get to use it for that. So why feathers evolved, we don't necessarily know. Part of the problem within that is that to get a good understanding of why feathers evolved, we would have to have a really good idea about when feathers appeared, what animals they appeared on, where they appeared, their number, and we don't have that yet, so we don't necessarily know. I'm going to leave the why feathers might evolve question. I want you to think about it, but I'm not going to answer it right now. We're going to do that in the talk on Wednesday because that will be a talk where we talk about the appearance of dinosaurs. And by default, I'm going to have to spend a lot of time discussing what would feathers have looked like, why did they look like that, and that kind of thing. So don't worry about that yet. Right, so I just mentioned this, but I guess I'll say it again. And then, of course, fossil feathers are easily identifiable to what modern feathers look like, and that suggests some very important elements about when feathers would have evolved. All right, so this is an early reconstruction of Archaeopteryx. It looks sort of like an awkward lizard with some feathers on it. And this doesn't mean the artist is stupid or didn't understand anything, but it reflects our understanding about that animal at the time. It's also doing this thing where it's like sort of holding its arms out to the side like it's doing a rave, or maybe it's doing the wave. But that is, that element, of course, is what you would not expect. The animal should tuck its arms in close to the body when it's not using them, and we now know that, right? And then the colors here are a little unusual as well. We don't think that's the colors that these guys would have had, and the head looks like a snake positioned on top of something like a bird body, but you can also see how long that neck is, which is reflective of the fossil. So just because you have a fossil that's articulated doesn't mean you necessarily get the best reconstruction. It takes a lot of work to figure out how each element of a picture. There's a lot of information in pictures, and it's really, really, really hard to draw an accurate picture, and it's really easy to draw an inaccurate one. So it takes a long time to decide how these animals are actually reconstructed. Archaeopteryx is a really interesting animal for a lot of people, and as a result, they've also looked at reconstruction of the body itself. This is actually a reconstruction of what we think that the animal looked like in life, and the colors are actually reflective of, to a degree, what we think the animal looked like as well. A couple of things going on here. One, that of course, as you would expect with modern birds, is the same. The head, excluding what is the beak region, is encased in feathers, and that protects the head. And then the legs, by and large, the leg is exposed. So in this animal, it's a little unusual. Actually, most of the leg is covered by feathers, but the lower portion of the leg is exposed, and that's because that's the portion that's going to get muddy. That's a portion that's going to run into stones, pebbles, rocks, and twigs when it's walking around, and therefore you don't want lots of feathers on it because they're either going to get stripped off or they're not going to provide the amount of protection that a nice hard scale will down on the lower end of the body. And this was a little bit unusual when we first identified it, that the legs are covered, right? A lot of the coverage of the leg, and look how many feathers are there, and they're asymmetrical, so those are involved to a degree with flight. That turns out to be because the earliest members of dinosaurs that probably took to the air were probably more like quadrupedal flyers in the sense that they look like biplanes. They probably didn't get enough lift from their front arms to provide really good lift, and so when they would jump or when they would come out of trees, they probably needed the additional lift provided by the legs, and that's lost relatively quickly because it's a lot of weight and you can't flap your legs. Those aren't very efficient.
I remember reading that there were at least two instances of flight in dinosaurs aside from birds, one of them being a microraptor, which I'm not sure if that was part of the
So there's a fair amount of debate right now whether flight evolved once or it evolved multiple times, and it's not clear which one it is. I suspect because flight is so difficult that had we considered the other groups evolving it, it's probably of a much lesser degree than we think of. The really true powered flight probably evolved really once, other members were probably doing something like gliding before that. And then this is probably, again, this is a little bit wrong because they've got the feathers all the way down to the toes. But again, probably a relatively realistic example of what Archaeopteryx would have looked like in life. So this is probably not dissimilar from what you would have seen. Keep in mind that it actually probably would have been more common walking around than flying. It just really doesn't have the musculature to provide long, powered flight. It doesn't have that big keel, and so it would have tired very, very quickly when it was in the air. And then the last piece, and we'll be done, there is actually dinosaur soft tissue, so TRex soft tissue that was found in 2006. It doesn't have DNA in it, but does have protein. If you take proteins and you record the order of the proteins, then you know the DNA code that would have reconstructed that, right? Because proteins are assembled by certain codes. If you then go back, now that you have what would be a reconstructed DNA strand, if you compare that to birds, of course, or if you compare that to all living animals, then dinosaurs should fit right in closest to birds and between crocodiles. Should be crocodiles, dinosaurs, birds should be the closest related. And of course, that's exactly where they landed, right? T-Rex falls in really close to aves, actually, when you look at its reconstructed DNA. And then, in fact, that means that we can actually recover soft tissue in rare cases from dinosaurs, and we may be able to reconstruct different segments of DNA from different animals. So this is actually the soft tissue of that animal, right? So they dissolve the muscle away, and they're left with these little collagen fibers. In fact, this is really cool. If you actually look at the pictures they have, they look like what happens when you dissolve bone today. They leave little networks behind of collagen fibers that support that bone, and you can see that very clearly. In fact, some of these, they had arteries that were also left behind, and they had what appeared to be little tiny red blood cells trapped within them as well. So there's actually a lot of stuff that they did with that. So the evolution of flight either occurred because of we have two large ideas about why this may have occurred. Either the arboreal hypothesis, where bird flight originates as birds gliding down from trees, and that flight develops as a way to land more softly or go up higher, or maybe as a cursorial, where you actually spend a lot of time running around and you use the flight musculature to provide longer and longer hops. So you're on the ground, you jump, you jump, you jump. And you can develop a little bit further. It may also have been used to provide them the opportunity to run up more and more angled surfaces. Flapping of the wings without flight is actually really still very, very useful for climbing near vertical surfaces or vertical surfaces. So animals, even birds that can't fly, will sometimes flap their wings, and that will help them go up into trees. So it's possible that's a way that flight evolved. And it's also possible that both of those were used in that sense, that dinosaurs were getting access up into trees, and it was helpful to get away faster, but also once they were up in the tree, it was helpful to come back down to the ground without walking all the way back down, just to jump down and glide to the ground. So maybe the two together in that way. Okay, so that is this lecture. So next lecture, which will be on Wednesday, will be about the appearance of dinosaurs, and that will include all dinosaurs, not just theropods, but we'll have the most information on theropods.